Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the matrices in special forms. In particular, we're going to talk about the diagonal matrices, the upper triangular and lower triangular matrices, and also the permutation matrices. We're also going to discuss about what kind of operations they do, and also we're going to discuss how we can construct them and how we can construct the inverses. So I would like to start away from the definition of a diagonal matrix. A matrix whose entries above and below the diagonal are going to be equal to the zero is defined as a diagonal matrix. So please note that we're not putting a constraint onto the diagonal entries, right? So there might be a zero or they might be non-zero. It doesn't matter. So the important part is that all the entries below and above the diagonal entries are equal to the zero. So for example, the identity matrix is a good example of a diagonal matrix, but it is possible that one of the entries on the diagonal matrix, so one of the entries on the diagonal might be equal to the zero here, or it is possible that all of the entries on the diagonal might be equal to the zero. So now what I would like to do is I would like to try to understand what does this diagonal matrix, what kind of operation it does, or what kind of operation this matrix does. So in order to do this, I would like to remind you about the three elementary row operations. And the first one was about the multiplication of a row into the constant, right? So before we do this, let's discuss about the multiplication of a row into the matrix. So what happens when you multiply a row into the matrix? So you need to look to this multiplication as a linear combination of the rows of this matrix. So essentially, of this row, it's going to be multiplied to this constant, and the second row is going to be multiplied to the second constant. The third row is going to be multiplied to the third constant here. Then we need to just add them. So essentially, the result of this multiplication is again a row where we are going to combine the three rows of this matrix. So essentially, the first element of the row of this matrix is going to be multiplied to the first row. The second element is going to be multiplied to the second row. And the third element is going to be multiplied to the third row. Then we just need to multiply a constant to the vector and just add them. And the result is going to be 2, 4, 6. So essentially, if you just multiply one row to the matrix, then you're going to get just one row again. So now what I would like to do is I would like to construct a matrix. So when only one of the rows is going to be multiplied to the 2, for example. Okay, so you see, so if you just putting 2, 0, 0, what it does is it just multiplies the first row here to the 2, and all the other rows are going to be the same, right? So what if I would like to multiply the first row to the 1? Then in this case, this vector would be just simply equal to the 1, right? What if I would like to multiply the second row to the 1? Then I would just get 1 in the middle here. And if I would multiply the third row to the 1, I would just get 1 to here. So let's put everything to the matrix. So essentially, what does this matrix is going to give us 3 rows. So the first row, what does give us the first row? It multiplies the first row here to the 2, the second row to the 0, the third row to the 0. And essentially just multiplies the first row to the 2 and giving us the multiplication of the first row to the 2. So what does the second row here is also giving us one row, and essentially just multiplies the second row of this matrix to the 1 and all the others to the 0, and giving us just the second row. And what does the third row of this matrix is again, it's giving one row, right? And in this case, it just multiplies the first 2 rows to the zeros and just give us the third row. So essentially, if you would just multiply the first matrix A to the second matrix B, what you would just get is the multiplication of the first row to the 2 simply. Okay, so the first row is multiplied to the 2, all the other rows are kept remaining the same. And you see what kind of operation does the diagonal matrix. So any diagonal matrix is multiplied to the matrix is going to be multiply a corresponding rows to the corresponding entries on the diagonals of this matrix. So essentially, I've got on the diagonals 2, 1, 1. And what does this operation to my matrix is that it multiplies the first row to the 2, second row to the 1, and the third row to the 1. So I'm going to get this matrix. So at the same time, now I would like to discuss with you the inverse operation. Okay, so essentially I've got this multiplication. If I would just multiply the yellow matrix as a diagonal matrix, I would just get the blue matrix. So now I would like to revert back to the yellow matrix. So essentially I would like to figure out a matrix which would just bring me my original matrix. So or essentially undoes the operation of that diagonal matrix, right? So what matrix I need to multiply this blue matrix in order to get the yellow one? So if you just look to these two matrices, I need to mention that only the first rows are different, right? And essentially I can get the yellow one from the blue one by just multiplying the first row of the blue matrix into the 1 over 2, right? And all the other rows should be the same. So essentially I will create another diagonal matrix where just first row or the first entry of this diagonal matrix is going to be equal to the 1 over 2, and all the others are going to be simply equal to the 1, because I don't want to change the third and second rows of the blue matrix. So essentially, this matrix is the inverse of my original diagonal matrix. So let's look to the previous diagonal matrix. So if you would just multiply this D to the yellow matrix, you would get the blue one. And now if you would just multiply the D inverse, right, to the blue one, you would get the yellow matrix. And my intention by this example is to explain you that the inverse matrix undoes the operation of the original matrix. And essentially, we can always check whether the two matrices are inverses by just multiplying them. And the multiplication of these two matrices is going to be equal to the identity matrix. And the last thing which I would like to talk with you about the diagonal matrices is the order of the multiplication of the diagonal matrix. So you see, so when you multiply a diagonal matrix from the left-hand side of your matrix, it is going to scale the row. So essentially, 2 means that your first row is going to be multiplied to the 2. 1 here means that the second row is going to be multiplied to the 1, and 1 here means that the third row is going to be multiplied to the 1. But what if the diagonal matrix stands from the right? So if the diagonal matrix would stand from the right, then those constants along the diagonal of the matrix would scale the columns of your original matrix. So essentially, this 2 would multiply the whole column to the 2. This 1 would multiply the whole column of this matrix to the 1, and this 1 would just multiply all of the columns here of this matrix to the 1. Then essentially, what you get is 2, 4, 6, 1, 2, 3, 1, 2, 3. Okay, so it is really important for us to understand this matrix multiplication. Whenever we multiply the diagonal matrix from the left-hand side of your matrix, then the rows are going to be scaled. If you decide to multiply a diagonal matrix from the right-hand side, then the columns of your original matrix are going to be scaled. So this is about the first elementary row operation where we would scale a certain row. So another row operation would be when we multiply one of the rows to the constant and add this into the another one. So this operation can be done also as a matrix multiplication. In this case, we're going to do this using so-called triangular matrices or so-called lower triangular matrix. So essentially, the definition of the lower triangular matrix is all the entries above the diagonal are equal to 0. So if you remember, the definition of the diagonal was like a below and above are 0, and for the lower triangular, so all the entries above are 0. So please note that then again, there is no constraint what should be the entries below the diagonal. There might be a 0 as well. And again, the constraint is all the entries above the diagonal are equal to the 0. So again, the identity matrix would be a good example of a lower triangular matrix Or so this example may be more intuitive, right? So because you've got non-zero entries here on the lower part of the diagonal matrix, of the diagonal entries. But again, so I mean, if everything is zero, it can be again considered as a lower triangular matrix as well, because it fulfills the requirements of the lower triangular matrix. So all the entries above the diagonal are equal to the zero. So now I would like to discuss with you what kind of operation does this diagonal matrix, the lower triangular matrix. Okay. So if you remember, we discussed about the elimination matrices, right? Or elimination operation. So essentially here, if you are given this matrix, what you would be interested in to eliminate the entry at the position 2 and 1. So essentially at the second row in the first column. So in order to do this, we usually write down this kind of operation or expression. Minus 2r1 plus r2. Essentially, what does it tell you is multiply the first row to the minus 1 and add this to the second row, right? And we have to do this manually. Okay, so especially if you would like to implement this in a computer, then it would be really painful because you need to just multiply one of the vectors to the minus 2 and add this into another vector and so on. So now what we would like to do is we would like to come with an elegant solution where we get the same result of the multiplication of the first row to the minus 2 and adding this to the second one by just performing one matrix multiplication. And again, we're going to use the combination of the rows, right? Okay. So what I would like to do is, again, I would like to figure out a matrix which would just make this operation of the elimination. And you see the first and the last rows are not changing, right? So do you remember how we can scale the rows? By just using the diagonal matrix. If it would be just simply 1, or let me write this with another color, 1, 0, 0, 0, or 0, 0, 1, what it does is it just multiplies the first row to the 1, the last row to the 1, and puts them instead of first row here and the last row, right? And now the only thing which is changing here is the second row. So how I can get this row here? By just multiplying the first row to the minus 2, by just multiplying the second row to the 1, and the third row to the 0, and adding them, I would get this row, right? So the multiplication of the first row to the minus 2 and adding this to the second one means just multiply the first row to the minus 2 and the second one to the 1, right? So we need to put here minus 2, 1, and 0. And this matrix does this operation. It automatically multiplies the first row, all of the entries of the first row, to the minus 2 and adds this to the second. And you see, so it's a lower triangular matrix, right? Okay. So if you would just multiply this matrix here, you would get exactly the elimination. So essentially, again, so if you multiply 1, 0, 0, it means multiply the first row to the 1, the second row to the 0, the third row to the 0. And just get one row and put this instead of first row because this three numbers, the combination, the numbers of the linear combination of the rows are staying in the first row. I would just copy 1, 2, 5. What does tell me the second row? It tells me, hey, multiply the second row, the first row to the minus 2, the second row to the 1, and the third row to the 0, right? So if you do this operation, what you get is here 0, 1, and minus 6. Okay, and I need to put this result to the second row because I'm taking the combinations minus 2, 1, and 0 from the second row. And again, the third row, the last row, what does it tell me is that multiply the first row to the 0, second row to the 0, and the third row to the 1. It just gives me the third row, 3, 4, 5. Good, you see, so we can do the elimination by just doing by just constructing the lower triangular matrices or upper triangular matrices as well. So now what I would like to discuss with you is how to get the inverse of this lower triangular matrix. So in order to do this, I would like to discuss with you the operations which we did. So essentially, we used to have the row 2, right? We didn't change the other rows so far. So what we did, how we changed the row 2 is that we just added the -2 row 1, right? So -2 row 1 times the R2 is going to give me this matrix. So the inverse of this matrix, what should does the inverse of this matrix? It should give me back the yellow matrix from the blue one. So essentially, again, so my original matrix brings me the blue one from the yellow one, and its inverse should bring me the original matrix. And if I look to this row, so I need to again get the R2. So do you know how we can get this R2? By just performing a similar operation, maybe. So what we did in order to get the blue one is that we just subtracted or added -2 R1 to the R2. And if I would like to get simply R2 in this row, what I have to do is I need to add 2 times R1, right? And that would be the inverse of this matrix. So again, what I have to do is I need to add to the second row the 2 times the R1, and it will give me the original matrix. So let me write this here. So the multiplication of the first row to the 2 and adding this to the second is can be done using this matrix, right? I have to multiply this to the blue matrix, right? What does this operation is that it multiplies the first row of the blue matrix to the 2 and adds this to the second row, and I will get the yellow one. So you see, so getting the inverse from the lower triangular matrices is not so difficult, right? So you just need to understand what kind of operations those lower triangular matrices does. So essentially, these two matrices are the inverses, and we can quickly check them by just multiplying them. So it is going to be equal to the identity matrix. Okay. So again, there is an upper triangular matrix as well. So the upper triangular matrices can also do the elementary row operations. But in this case, like it was like, if you remember, we used to have the Gauss-Jordan elimination, right? In the Gauss in the Gauss step, in the Gauss phase, we always went from the upper rows to the below, right? And in the Jordan step, we always went from the lower rows to the up to the top. So essentially, the upper triangular matrices can be used in order to perform the Jordan elimination. But the idea is going to be the same. And the last, so here are a couple of examples of the upper triangular matrices. And the last operation which I would like to discuss with you is the permutation. The permutation is essentially just flipping around the two rows. For example, if I would just change the first row, interchange the first row with the second, I would just write it down. Hey, just interchange the first row with the second, and I would get the following matrix. And again, what I would like to do is I would like to do this in a more elegant way by just multiplying this matrix into another one, which I'm going to call as a permutation matrix. And again, the idea of getting this permutation matrix is a linear combination of the rows of this matrix. So you see, so what is the same between these two matrices is that the last row are the same, right? So I would just copy this, like I would just put here the numbers 0, 0, 1. And do you remember what does the 0, 0, 1? So again, so whenever you're multiplying this matrix to your original matrix, it's a combination of the rows of your matrix. Okay, so essentially these three numbers 0, 0, 1 are going to multiply the corresponding rows of the original matrix and just sums them. So 0 multiplied to the first row, 0 multiplied to the second row, 1 times to the third row is going to give you exactly the third row, right? Now, in the second row, what I have to get is, so you see, so this row is the first one of this one, right? What I have to put here on the second row is that 1, 0, 0, right? And again, it multiplies the first row to the 1, the second row to the 0, the third row to the 0, which is essentially the first one, right? And brings me here to the second row. And what I have to put here on the first row of this matrix is the second row of the original matrix. So how I can get the second row, just solely the second row of the original matrix, by just multiplying the second row to the 1 and all the others to the 0, right? So if you would just multiply this matrix to your original matrix, it would just flip the first and second rows between them. So again, if you would just implement and try to implement this using the vectors, then you would need three vectors, right? So you would need one buffer vector, where you would just copy the second row to the buffer, then copy the first row to the second row, then copy the buffer to the first row, and so on. And you can do this in a more elegant way using so-called permutation matrices. And again, if you would just multiply this permutation matrix to your original matrix, these first two rows are going to be flipped around. Now let's discuss a bit about how we can get the inverse of this matrix. And again, the inverse, what does it mean, the inverse? Is that so I need to multiply the blue matrix to such a matrix in order to get the yellow matrix, right? So how I can revert the blue matrix into the yellow one? By just doing the same operation, right? I got the blue one by just interchanging the rows of the yellow one, and I can get the yellow one by interchanging the rows of the blue one, right? And essentially, the inverse of the permutation matrix is itself. So amazing. So you can just multiply a matrix to itself in order to get the identity matrix, right? So let's make a summary. So we've learned about the three operations, row operations, can be done using the matrices in a spatial form. We've learned about the diagonal matrices. So the diagonal entries of these matrices are going to scale the rows correspondingly. So especially this matrix, what does this matrix is that it just multiplies the first root as a 2. So we've also learned about the lower triangular matrices or the upper triangular matrices. What does those matrices are essentially just multiplying a row as a constant and adding this into the other one. Especially this one is multiplies the first root as a -2 and adds this to the second, and by keeping all the other rows the same. And we also learn about the permutation matrices. What does the permutation matrix is to interchange the corresponding rows, right? For example, this matrix, what does the permutation matrix here is that it interchanges the first row and the second row. Here are three elementary row or elementary matrices. We're going to later on discuss how we can combine these elementary matrices in order to decompose the matrices into the LU decomposition. So I hope this video was helpful. Thank you very much for your attention.